여러분 안녕하세요. 저는 Markku입니다. Sorry, my Korean is very, very limited. Sorry. Anyway, I'm a solutions architect. I try to help our customers use Google Cloud. And I'm joined here with, you will see him soon, Ajay, who is the product lead for Edge Machine Learning and Edge TPU. So today we, with Ajay, would like to show you how to do automation of industrial inspection with Google Cloud, with specifically something called AutoML Vision and some interesting hardware as an option as well. Let's first talk a little bit about how to do machine learning. I don't know TensorFlow. I'm admitting I don't know. So I like to consider myself as a kind of normal developer. So I'm not a data scientist. I want to use machine learning, but I don't know how to build machine learning. So I like these two things here. So on that side, we have APIs. Those are the easiest way to actually use machine learning. Google has collected a lot of data, a lot of images, etc. And we have trained pre-trained models. So we have made machine learning models that are very high quality, and we have been improving them over a long time with a lot of computation and number crunching. And now you can use those pre-trained models very easily. It's literally 2 lines of code. First line is that you load the client. If you use Python, whatever language, you load the client for the machine learning API. Second line of code is that you send your data, you send your picture, your link to your video, or maybe an MP3 file of somebody talking or WAV file, and you get back a response. The inference is running in the cloud, in Google data centers, and you get back a response that in your picture there's a cat and a dog and a hamster, for example. So that's the easiest way to use machine learning. If you can use the pre-trained models, you can get going immediately. The same day you can start using machine learning. But quite often you have a custom problem. You have a unique problem. I don't want to know between cats and hamsters. I want to know which cat it is. This is Bobby, this is Skippy. I want to know, is this a bad credit card transaction? Is this a good credit card transaction? So you may have custom problems where you need your own machine learning model. That's where AutoML is helping. So with Cloud AutoML, we literally have machine learning creating and optimizing your machine learning models for you. And the way that works is very simple. You provide it example data, and it learns from the example data. You say, these are pictures of object A, and these are pictures of object B. And it will learn the difference automatically and give you a model. And then you can run the model in the cloud or even somewhere else. We will show you soon. AutoML has a very nice to use interface. It's basically a web wizard where you just click through and you say, these are my example images, these are whatever my example data. And at the end of the wizard, it will give you your model. If you do, for example, image recognition or classification, you can even get object detection. Where in the image is your hamster? But when it comes to real manufacturing and industrial use cases, real enterprise use of this technology, then there's many use cases. If you are manufacturing some components or maybe making cars, you want to know in your production line, are they good? What is the quality? Do I have any defects? Do I have any issues? Do I have any missing parts? Is something installed wrong? And until now, you had to use humans to do that. And this is slow, and it doesn't really scale. And it would be better if the humans would do something more valuable. So machine learning and AI can be used here to scale and at great speed and great accuracy do something like visual inspection. Another one is the green point there, predictive maintenance. So if you have an industrial system, maybe you have some large machinery, you don't want it to break down. If the machinery breaks down, you have an outage and then your business suffers. So what you can do is instrument the system, put sensors there. Maybe they already have sensors. You collect the data, and then you can do predictions with machine learning. And you can predict that based on these numbers here, it looks like your gearbox is starting to heat up, or your engine will shut down in 2 weeks because we can see the gearbox is having issues. Then you can schedule the maintenance and replace the equipment without any downtime. And of course, safety is really important. So you can then have automatic visual inspection of things like airports or traffic where a lot of machinery are moving around, and you can prevent problems that might even hurt people. So it can increase safety. The thing to know is that when you create a machine learning model, the model is created on data. If you make a custom machine learning model from your data, you own the data. Nobody else has access to the data, only you. Google doesn't use your data for anything. It's your data. It's accessible only by you. And you can, of course, anytime delete your data and your models. Now I'd like to show you a short video of one of our customers called AES. It's an energy company. And you will see in the video how they use this technology.
Global warming is one of the big challenges of our times, if not the biggest challenge of our times. Now, we really do have the technology to address the issue of carbon footprint greenhouse gases from the electric sector. The AES Corporation is one of the leaders in new technologies for renewables and energy storage. It's a Fortune 500 company. Our mission is accelerating a safer and greener energy future.
Right now we have around 8 wind farms. Each farm has different capacity, starting from 50 turbines up to 300 turbines.
They cover large spans of geography and land. They're spread across hilltops and mountainsides.
All these turbines need annual inspections. Originally, it could take up to 2 weeks to do one inspection. We partnered with leading drone service company Measure. Right now with drones, we can do it in 2 days. And this is safe and quick.
For a wind turbine inspection, we go out with our pilots, and what we're looking for is cracks or defects, things that may need to be repaired.
On a typical inspection, we're coming back with 30,000 images. Spending 4 weeks reviewing images, I don't think anyone's going to argue that that's the best use of a highly trained engineer's time.
How do we speed that up, and how do we make it 10x more efficient? That's where machine learning and AI comes in.
We've built a great end-to-end solution using Google Cloud's tools and platform. With the AutoML Vision tool, we've trained it to detect damage. We're able to eliminate approximately half of the images from needing human review. The remaining 50% of their time can now be very focused on identifying that damage and really determining the right course of action to remediate it. Moving from reviewing images to training machine learning models, it's a much higher order employment opportunity for people, and one where we're trying to develop our team. Google Cloud has been a great partner. Their technology is consistently among the world leaders, and they're just a great partner to work with person to person. At the end of the day, we won't reach the cleaner energy future without advanced tools like machine learning.
Technology will allow renewable energy to be cheaper than conventional energy. Artificial intelligence, robotics, this is really what the future's all about.
All right, so that's AES. It's really cool, right? Automating the drone flight paths, taking tens of thousands of images and then analyzing any problems in those huge turbines automatically with AI. So they get a lot of business savings from there. Obviously, it's a lot more scalable, and also the accuracy is better than humans can have. It's fully running on Google Cloud, and the heart of the solution is really AutoML Vision, having a custom model for this particular problem, which are these different problems in those turbines, like lightning strike leaves a specific mark. The next steps that they and many other companies are looking at are, for example, segmenting aerial images, like there's a potato field here, and these are cabbages, and then understanding the difference between healthy cabbages or very dry soil or too wet soil, etc. Also looking at different kind of frequencies of light. So the normal cameras that you are used to are not the only type of cameras. There's also infrared cameras and ultraviolet cameras, LiDAR, which is a laser rangefinder that can still produce an image. So using machine learning to analyze those different types of frequencies and wavelengths can enable companies to do even more visual inspection, not just visual light that we are used to. One example of this is LG. You all know LG, right here in Korea. So LG CNS manufacturing a lot of displays, monitors and TVs. So when LG used humans to inspect these new TVs or monitors on the production line, the accuracy was about 60%. And it takes a highly trained eye to do this. Obviously, it's quite slow because humans don't work as fast as computers. So by using AI on the edge in the factory, they can get a significantly higher accuracy, up to 99.9%. And then that kind of machine learning visual inspection at the production line could save them up to $20 million per year. So the business savings and speed and scale improvements are immense. Now that's an example of an edge machine learning. Edge meaning that the machine learning happens right there, maybe in your factory, in your production line, in your house. When you do that, sometimes you need to process the data. So sometimes you need to do a bit of pre-processing, for example, to detect good cookies from bad cookies. You may need to do some image filtering, either yourself or with partners. It depends. And then ultimately what you want to do is to run the machine learning, in many cases, in your factory, in your production line. And to do that, we have an interesting end-to-end solution here. So first, you ingest your data. So with any machine learning, you need the example data, right? And then you may be able to label that example data that these are pictures of good cookies and these are pictures of bad cookies. If you are not able to label them yourself, we have a labeling service, which is humans labeling your data based on your requirements, and then you have these labeled examples. Those labeled examples are crucial, they are critical to create a good machine learning model. Then AutoML Vision, in this case, there's different flavors of AutoML, but AutoML Vision will then learn the difference between your labeled examples. And then the funny thing is that you can export the model. You can run AutoML in the cloud, you can send your data there, but if you don't want to send the data there, you can export the model from AutoML, your model, and run it anywhere you want. For example, on edge devices. And to talk about the edge devices, please give a warm welcome to Ajay, who's the product lead of Google Edge ML.
Thanks, Markku. Hello, everyone. My name is Ajay Nair. I'm the product lead for Edge Machine Learning at Google. And we are bringing out a new product that was introduced a few months ago called Coral. So before I talk about Coral, some background on machine learning hardware itself. So Google, a few years ago, productized machine learning hardware called the TPUs. It's Tensor Processing Unit, which was available in Google Cloud, and GCP customers can make use of that by renting compute on that infrastructure. It's been available for 4 years now. A lot of our customers came back and said they would like to run machine learning at the edge. And what they mean by the edge is anything outside of the cloud. So we, similar to the cloud TPUs, designed a chip bottom up just for machine learning, but a smaller form factor, lower power devices that are designed to live outside of the cloud. And by the edge, it could be on-prem data centers, gateways, or sensor-level devices. And those are being brought out through the Coral platform. So one of the key requests from customers that led to the Edge AI is the use cases. So customers came to us and said there are many reasons why they want machine learning at the edge. I'm showing a few of those here. One is privacy. So if you run inference at the edge, you don't need to take all of the data to the cloud, which might either be not allowed in certain countries based on regulations, or just has privacy concerns. The other one is latency. Sometimes you need to make a decision immediately. You cannot afford the round-trip latency of sending the data to the cloud and then taking a decision there and sending the decision back to the edge. So that may not be, that might be slow. The one important example was bandwidth. So in many use cases, specifically if you talk about a camera, a always-on 4K camera produces about one frame is about 24 megabytes of data. And you need about 30 frames per second for any useful information without jitter. So at 30 frames per second, we're talking about 700 megabytes of data in 1 second. So if it's an always-on 4K camera, which is on 24/7, you can imagine the terabytes of data that you are having to stream to the cloud and then store in the cloud. And then when you run machine learning, you have to do machine learning on so much of data, out of which useful information might be very little. So if you run inferencing at the edge, you can stream only useful data. So you're saving on bandwidth, you're saving on storage cost, and when you need to extract useful information, the density of useful information to the total amount of data is very high because you've streamed only useful information to begin with. Another need that customers came to us was need to be offline. For example, the wind farms that we saw, right? They might be in geographies where there's no internet connectivity, or there are oil rigs, or third world countries where internet is not available all the time. So you need to run inference locally without any connectivity to cloud. That was another use case. And finally, cost. The cost of streaming data, the cost of the actual hardware, as well as the cost of how much power you need to run inferencing at the edge. So for these reasons, Google looked at what we can do to enable an inference device. And one of the key things to remember is that for all those needs, you do require a lot of compute at the edge as well. As a simple example, if you take a 224 by 224 section of an image and run a MobileNet V2 model on it, which is a lightweight model, you need about 120 million operations per second to get about 60% accuracy on that small image size. For the machine learning practitioners amongst us, we know that 60% accuracy is not enough, right? So if you want to get up to 75% accuracy, the amount of compute needed is 10x more. It goes to 1.2 billion operations per second. And of course, even 75 is not enough these days. We need close to 90% or above 90% accuracy, which means we would need another 10x, about 12 billion operations per second. So typical hardware that is available in edge devices cannot perform those many operations because traditional CPUs are designed for a different kind of task, not too many operations. They're designed for more complex but less number of operations. So you do need a specific hardware accelerator for these edge devices. And for that, Google built the Edge TPU. So the Edge TPU is an inference accelerator. It was designed, it's been in our labs for a couple of years. It's a 4 teraops, so it's not as powerful as the cloud TPUs, but it's very power efficient. It's 2 watts for the 4 teraops, so roughly about half a watt per teraop. And it supports Int8 and Int16, which means that your machine learning models need to be quantized to be able to run on the Edge TPU. And it provides very efficient performance on your machine learning models. For example, for a MobileNet V2, you can easily get up to 300 inferences per second. And we have adopted TensorFlow Lite, which is Google's framework for running machine learning models on edge devices by making them more efficient in terms of the memory footprint as well as the performance needed. The Edge TPU is available to customers through the Coral platform. So the idea with Coral is to allow customers to go from prototyping their ideas, to think about their ideas, prototype it, deploy it for a proof of concept, and then actually take it to production, all with the same framework of hardware, software, and tools that are available. You can check out Coral.ai. It's a Google product that's been available. So what is Coral? The idea was, I mentioned 5 reasons why customers asked for edge machine learning: privacy, performance, efficiency, etc. So Coral is a local AI solution of hardware, software, and tools to allow customers to bridge that gap and run machine learning at constrained environments of the edge. The products that we have available today are shown here. So on that side is a development board, which is available now. And that is essentially a single board computer which takes the edge TPU, and we connect it to an industrial grade NXP system on chip, which is a quad-core A53. And all the peripherals that you might expect from a single board computer in terms of HDMI outs, maybe camera inputs, Wi-Fi, Bluetooth, Ethernet, stereo in, audio mic inputs, etc. And it's a full single board computer with its own operating system. So you can actually bring your machine learning models, as Markku mentioned, either your own models or through AutoML, and run it on there. What we see in the middle is the Pci Accelerator. So it's the edge TPU available either as an M.2 or a mini Pci form factor that you can plug into existing systems. So if you have a host system which has a mini Pci slot or an M.2 slot, you can plug these in to your system. It would look like a Pci endpoint, and you can run your machine learning models on those. We have the Pci runtime drivers available. Similarly, we have the USB thumb drive form factor. So that's looks exactly like a USB drive. You can plug it into your existing PC or workstation or your device, which has a host controller, and it'll show up as a USB endpoint, and you can accelerate your machine learning workloads. We also have the system on module, which is essentially the same component which is under the fan and the heatsink here. So we are providing that as a product to customers, and we are also making the design of the base boards available, the schematics. So if a customer would like to, they can integrate the system on module in their own baseboard and choose to bring out only the signals that are required for you in the form factor that is required by you. Right? So all of these products are available today, and in the Korea market as well. The development board and the SOM are available through Seed Studios, and you can buy them right now. And the accelerators, the USB and the PCIe, are available through either Seed Studios or Mouser. And the idea is just accelerate your machine learning workloads, get your proof of concept into these devices, and as well scale to production with the same components, the same software, and the same tool chain as needed. In terms of performance, we analyze the performance internally with what it gives users. So what you see on this side of the chart is a comparison of running different model architectures. So what you have on the axis, the y-axis, are the different types of machine learning models that we have run on our hardware. What you see on the x-axis is the inference time, which means lower is better. The blue bars are when we run these models on the desktop CPU. So this is standard Google-issued desktop CPUs that our engineering team uses. And the desktop CPU is a Intel Xeon running at 3.6 gigs, so it's a very powerful CPU. Now, then we enable the edge TPU, which is the USB drive connected to the USB port, and run the same models, and you can see the inference times are really greatly reduced, especially for the models that fit within the memory that is available on the edge TPU, which are the ones in the middle. You can see that it's really, really small inference time, up to 3 milliseconds for a MobileNet V2, which equals about 300 plus inferences per second, which is great for a tiny device that consumes so low power. For models that don't fit on the onboard memory, there is some I/O penalty that you pay on going back through USB to fetch the remaining part of the model. But as you can see, still it is much better than running it on a really powerful desktop CPU even. What you see on this side is essentially running the models on the dev board that we showed earlier. So first we run it on the A53, which is not bad. It's a quad-core A53, so it is a powerful CPU in that respect. But then when we enable the edge TPU, it actually, you can see the performance difference. It's almost 100x better in some cases in terms of the latency that you notice. So it gives you a chance to understand how efficient the edge TPU is. And if you have use cases and existing models, it's pretty easy to get one of these devices and test your devices, test your models on these devices to understand what kind of performance you can see. And in terms of the machine learning models themselves, Markku touched on a little bit. There are multiple ways that you can get your machine learning models running on the edge TPUs. One is customers' own data and customers' own models, right? So, the first one is Google's own data and Google's own models. So we have some pre-compiled models that we have referenced on the Coral website. Again, that's coral.ai. So they're pre-compiled models for object detection, segmentation. We have some keyword detection model that you can use and test and get off the ground. The second aspect is you can use those models and do something called transfer learning. So transfer learning is where you just retrain the last layer of your machine learning model with your data set. And that is a very efficient way of learning machine learning without needing deep expertise. And we also have AutoML. Markku talked about it a lot. He will come back and show a demo based on an AutoML inferencing running on the edge TPU for a real use case. Finally, we have where if you have expertise in machine learning, you can just use Google infrastructure for training your models. So you bring your own models and train on Google infrastructure. There are software tools that the Coral product comes with. It's not just the hardware. So we have our own Mendel operating system that is a variant of Debian. So that sits on the CPU. We have our C++ and Python SDKs that export APIs for customers to use. So after inferencing is done on the edge device, what do you want to do with that data? So you have APIs to enable you with that. There's an HTTPU compiler and companion software that is also available. And the website is designed to be very user-friendly. So please, I would encourage you to just look at our website, look at some examples to get off the ground with machine learning. The whole idea with the edge TPU and the Coral product family is to enable an end-to-end ecosystem, not just for inferencing at the edge, which you can do, but to connect to the rest of the Google ecosystem. So what I'm showing here is if you need labeling service, as Markku mentioned earlier, there is labeling service that Google provides. Then you can take that data from Google, the labeling service, feed it into AutoML, and AutoML will generate an edge TPU specific model for you, which is TensorFlow Lite, compiled already to run on the edge TPU. You can deploy that through Google's solution for IoT called Cloud IoT Core, and through that you can deploy it onto the edge device, to the Coral device. You can run your inference locally through the APIs available, take actions as needed for local compute. And then you can, based on some data, for example, if you have a person detect model, and you want to stream the number of people that are there in a room at any given time and want to see it in a console, you can stream that data back through Google's managed services, and you can analyze your data. You can also use that data to retrain your models. So you can feed that back into the Google AI ecosystem to retrain for storage, for retrieval, for data analytics. And then you can, after retraining, push that through IoT Core back into the edge device. So it completes the loop where you can do end-to-end training and inference, and then retraining in a loop for your application. So recently there was, we updated our website with a few customers who came up with some use cases. Very quickly, there are two of them in healthcare. So Virgo is a company that is using edge TPU connected to a camera in an endoscopy procedure to help the clinician identify ulcers in the stomach when the camera is put in, right? On the other hand, we have Care.ai, which is a healthcare startup. So they are putting cameras in hospitals and homes to do two main use cases for now, and they're expanding. One is to detect falls. So when people fall down, there's a pose estimation model that a person is falling or has fallen down, and you can alert the nursing staff to take care of them. And also for bed sores. If a person who's admitted in the hospital is not moving sufficiently in a given amount of time, you can create alerts and people can take action based on that as needed. In the middle is a very interesting use case of a company that does water meter readings for industrial applications to find out if there's a difference between the actual reading in a water meter versus what the vibrations of water flowing through the pipe is telling you. So there's a model that they created for that. They run it on the edge TPU, and they've been able to save the city of Atlanta millions of dollars in lost revenue. But those are just some examples that are on our website. The potential uses of machine learning at the edge are across multiple industries and multiple use cases, from scientific research to education to automotive, in terms of either fleet management or for driver recognition, in consumer appliances, in industrial robotics, we'll talk about that, in agriculture to identify different types of products and different types of crops. In healthcare, we saw that already. So it's just the tip of the iceberg. It's just up to your use case. If you have a use case, you can enable that and run those on Google's products, and you can get our help with either creation of the model or running those efficiently at the edge. So in summary, Coral is a platform of edge machine learning hardware that brings inferencing at the edge, but also ties multiple other Google products together and enables customers to bring all of that under one umbrella, right? So you can train with AutoML, connect through Cloud IoT Core, use either precompiled models or your own models, convert them to TensorFlow Lite, and run them on the edge TPU. So I'm hoping that many of you would want to use the edge TPU and experiment with your machine learning use cases. And if you have any questions, we do have a support channel at coral-support@google.com. Feel free to reach out. Check out the website, coral.ai. There's a lot of useful information. It is designed for people who do not have much experience in machine learning. So if you don't know anything about machine learning, you can still go there and learn a lot. So with that, I'd like to hand over to Markku, again, to come and show a real-life use case on how we've used edge TPU for an industrial setting. Thank you.
All right, thanks, AJ. So now, to end the session, I'd like to show you a real customer use case. And I was the one working with the customer part of the team, so I know this case intimately. So it's with Kyocera. So this customer use case is that Kyocera are manufacturing components. They have a production line. They make these kind of little components. And they need to know, are they good? Do they have any problems? Are they good quality or bad quality? Now, there's a little problem. You can see these are actually some of the original raw images from the camera on top of the production line. What we are interested in is the component in the middle. There's one component in the middle. That's the one we want to inspect. But you can see in the camera image, there's a lot of other components visible. So there's a problem there. And the main component in the middle is jumping around. So that's confusing for the machine learning model. So what we had to do was a bit of pre-processing. So when we started with just the raw images, without any pre-processing, the results were not good. They were like 17% machine learning model quality, so not good at all. So we had to improve the raw data, the training data, to create a better model. And then how did we do that? The first step is this. So I went from this full image. I wanted to cut out the edges. I wanted to cut out any unnecessary information. So I did a crop. So I just found a place in the images. If I cut the images here, we still have the component in the middle, but we don't have anything extra. We don't see any other components. But you can see that there is still a problem that the crop is not perfect. And the image is tilted. You can see the object is actually not straight. And by the way, what we want to create is a machine learning model that detects those problems. So that's what the machine learning model has to see. It has to know, are there issues like that inside the components? And the issues are so small, and they can be anywhere here inside the component. So without the pre-processing, the object was jumping around, and then the machine learning model was confused, like, I don't know what to look at. I don't know. So we have to help the machine learning model. Next thing I wanted to do, step number 2, is I applied some image filtering. By the way, I did this with Python because just my language, I like Python. And Python has a lot of helpful libraries and modules you can use. So I found some image processing libraries that, for example, let me remove the background. So I applied an image filter. I tried different options. And with this image filter, the background goes to 0, 0.0.0, so black pixels. So all the background pixels have 0 value. In the other way, only pixels in the image that have value belong to the component. So that filter was good. It got rid of the background. Next, I applied step number 3. Now that we only have the image, the object visible here, I'm able to apply a filter that gives us the edges. Now, why am I interested in the object edges? 2 reasons. I want to know, is it tilted in some way? I want to fix the tilt. And then I want to crop again very tightly. To detect the angle of tilt, I used something called Hoof Transformation. So basically, with this image, with the edges, I apply to this image the Hoof Transformation, and it's able to detect lines, continuous lines. In this case, the object has some straight lines. So I'm able to get these lines, and then I remove outliers. Sometimes it's not perfect, so some of the lines are not exactly correct. So I do a bit of cleanup for these lines. I remove lines that are conflicting with the other lines. So I remove the outliers. And I'm left with these lines that are telling me the angle of tilt. So let's say that it's tilted by 2.34 degrees. Then what I do next is I counter-rotate the object, minus 2.34 degrees. Then the object is 0 degrees. Rotated, it's flat. Why do I do that? So that the next and final step is this. When the object is straight, I do one more crop. And now, after this, was it 5 steps, 6 steps image processing, we are left with only the object in the middle, and it's straight. So now when we look at the objects, these are the actual pre-processed images from Kyocera. You can see that the object is not moving around anymore. It's pretty much stable. Now the only changes between the images are those defects. Or if there's no defects, then it's a good object, right? So when we did this pre-processing, and then we gave the data to AutoML, now this was the result. We got 95% accuracy and 98% accuracy at detecting good and broken components. So this was good enough for the customer. It meets their requirements. And also the speed. Then we exported the model from AutoML. AutoML created the model. We exported it. We executed the testing on the Edge TPU on the Coral board. And the average inference time is only about 9 milliseconds. So it's very fast. So now I would like to show you this demo. So let's switch to my laptop, please. And here we are. Okay. So now we are on my laptop. I will show you 2 things. First is the pre-processing, and second is actually running the inference here on the Coral dev board. So step 1. We have one of the original actual images from Kyocera factory here. I just opened it in the preview in my Mac. So you can see that here we have the component in the middle, but you can see it's not straight. It's tilted a little bit. So if I now run the pre-processing script that I talked about against that image, let's see what happens. So now it loads that original image, and then it starts filtering. So we can see here some edges. We can see some filtering that removes the background. And then we can see the Hoof transformation. So once we have removed the background and we have made the edge detection here, wireframe, we feed this image into the Hoof transformation, which is then detecting the lines. I calculate the angle of the lines, and then based on the angle, I rotate the image minus the angle, so then the object becomes straight. And then I crop one more time. So then this is the final result. So it's a nicely cropped object, and the object is not anymore tilted, it's straight. So this is then one training image for AutoML. So I executed this same script, same processing against all the training images, and I got these nice training images that gave us the good result in AutoML, so 95 and 98% accuracy. So then after that, AutoML trained the model, tested the model, and we exported the model. And now we are here. The second demo then is running the model that AutoML created here on the Coral dev board. So this one is a little bit like a Raspberry Pi, but it's not. It's made by Google. So Ajay was talking about it. It's a single board computer. There's a CPU running Debian Linux, Mendel flavor, and there's the HTPU processor inside. So what I did was AutoML gave me the file, the TensorFlow Lite model for Kyocera. I literally copied the file here, and I copied also the Kyocera raw images here. And then what we can do now is this. On the HTPU, on the Coral dev board, I can execute then running the model against all the Kyocera images. So let's first run the model against the known good images. We know that this folder of images has good quality components. So the machine learning model should say OK as the result, right? So let's see what happens. I will run it now. So one by one, this board is loading the image, running the machine learning model, and doing the inference. I know it looks a bit ugly, this output, but let me explain what we have here. We have the image that was loaded, the inference result, which in this case is OK, which is good. We know it's a good component. Then the confidence value. So how confident is the machine learning model that this one is a good component? And then finally, in milliseconds, the inference time that the HTPU took. So it looks great. So machine learning says, OK, OK, OK. We know that these are OK components. But I just want to show you something that it's not 100%. Here, for example, this one line here shows a mistake made by the machine learning model. So there, the machine learning model is saying, that's a broken component. It's not. It's not. So it was not 100% accurate. It was 98.5% accurate. So most of the time it was right. But interestingly, when machine learning made a mistake here, because it's shades of gray, you can see that the confidence was 0.5. So the machine learning model was not very confident. So then what you can do in your application side is you can say that, OK, I don't trust machine learning inference results where the confidence is low. So then you set a cutoff value. Maybe you only take results that are at least 70% or 80% confident. So you can see here that in the mistake, the confidence was low. I will run one more thing, which is let's analyze all the known broken components. So I have another folder of Kyocera images. We know that they are examples of bad components, so components with defects. Run them against the model in the HTPU. You can see here NG, not good, not good, not good most of the time. But we also see one mistake here. Here, the machine learning model said that, yeah, it's a good component. It wasn't. So if I remember right, we have 95% accuracy for these, or 98.5, depending on what you're detecting. So here we have a machine learning mistake, and we can also see that the confidence was quite low at 62%. But overall, like I mentioned, we got 95 and 98.5% accuracy. So that was good. All right. Let's go back to the slides, please. So just to recap what you saw. So the demo that I just showed you the live demo. First, we have the raw image. Then we use this Python pre-processing that I made to get this nicely cropped object that is not rotated. That was running on the CPU of the development board. And once we have this cropped object, we then use the machine learning model that AutoML created. We run it on the Pci Accelerator here. We give this cropped image to the machine learning model, and the machine learning model is just giving us a binary label, OK or not good. OK or not good. So that's how it works. Machine learning was used just as a labeling machine there. So I really hope that you enjoyed it. Kamsahamnida.